In this video, I wanted to talk about complex roots of polynomial functions, and I wanted to start off by talking about the complex number system, reviewing some of those basic properties, and the historical significance of imaginary numbers. I remember when I first learned about imaginary numbers in high school, I thought it was kind of weird and interesting, and so forth, but I didn't really necessarily grasp the significance and the value of those number systems at the time. So I wanted to, start off with basics and kind of discuss a little bit of history here, and then get into a lot of the theorems and how complex zeros factor into a lot of these things regarding polynomials that we've been talking about. But very, very early on in math, with very simple polynomial functions, mathematicians realized that some polynomials had issues. Like, say, for example, a very historically relevant polynomial problem, x squared plus x plus 1 is equal to 0. Originally, it was a polynomial which was said to have no solution. And even today, a lot of people will say, well, sometimes people will say imaginary numbers mean no solution, which is not entirely correct. It's kind of a matter of perspective. But, if we were to apply the quadratic formula at the time, the quadratic formula was not known. And even once the quadratic formula was determined, it still resulted in a problematic result, which mathematicians struggled to deal with for hundreds of years. Basically, we'd have, negative b plus or minus b squared minus 4 times a times c, all divided by 2a, which would give us negative 1 plus or minus the square root of negative 3 over 2. And the issue here is the discriminant, the value within the square root in the quadratic formula, was a negative number. And negative numbers within a square root create an issue where no real number can square to make a negative. So historically, a lot of mathematicians said, well, this is a dead end. There is no way of doing this. We cannot solve this. And that is not entirely wrong. It's just not, basically, it's revolving around a mathematical system where we do not understand how to take the square root of a negative. So basically, how we know today is that the square root of a negative number can be defined by the imaginary unit, which represents the square root of negative 1. If we factor out the square root of negative 1, which we often call I, the imaginary unit, we can rewrite this expression as what we refer to as a complex number, a number which has a real component and an imaginary component, together making it a singular number, which is a complex number. A lot of times we write it as a plus bi to represent the components. And complex numbers are complex, again, not to be silly, because they have two different components, but together they make up a singular number, a singular complex number. And basically what I was saying is originally mathematicians had a problem with this. They said it was a dead end. But in the early 16th century, certain mathematicians started to deal with that problem in an algebraic manner. And the first person to really use I and define how to operate and work with I in a mathematical way was Raphael Bombelli, which was really a tremendous breakthrough in mathematics, and also had tremendous implications to physics and lots of other of the natural sciences. And I wanted to kind of touch on that for a minute. But basically he defined, well, how do you multiply? Say I had 3 plus 4i and I wanted to multiply by 2 minus 7i. He kind of fleshed out the math on how that all worked. And the whole coinage of these numbers as being imaginary, it was originally a derogatory term, because imaginary, as the term suggests, implies that these numbers are kind of made up. They're fictional. They're not real, right? All of those are terms that we still use to define imaginary numbers. And this is actually a big problem. And in my mind, I encountered the same problem in high school, because when my teachers, were talking about imaginary numbers, I thought to myself, okay, imaginary, it can't really be important. It sort of seems silly, and it lost the importance of the numbers. But in actuality, when I started studying physics in college, I started to realize I is a really important number. It's actually in a lot of real equations. And if you're going to understand physics in advanced levels of science, you really need to have a pretty good understanding of what I is. And actually, there's kind of an interesting parallel here with like negative numbers and zero. in the scope of human history, 0 did not always exist as a number. Today we use it regularly, but the idea of nothing, when you're and you can kind of imagine when you're a kid and you're learning to count, most kids don't count by starting with 0. They start with 1 because they understand the idea of a whole number and what that represents. But 0 is an abstract concept which was not widely accepted as a number, sort of like I, and what I'm getting at here. Even like fractions and negative numbers as well. If you think about the term negative, it has a negative connotation. Again, I'm not trying to be silly here, but positive is good, negative is bad. And these names can lead us to believe that these numbers are not useful or important. And it's just because the English, the way that it developed when they first were being used and created, they weren't thought to be necessarily useful or relevant. And René Descartes, he's a mathematician who did a ton of work with polynomials, and he actually developed some of these theorems, helped develop some of these theorems that we've been learning. He was in the camp of imaginary numbers are not useful. They're not really good, and we should not accept them as something in math, which turned out to be one of his fatal assumptions because of how they obviously have proved to be so useful as history progressed. So I wanted to define the imaginary unit a little bit as well. And it's often presented in either of these two ways. I is equal to the square root of -1, as I mentioned a little bit earlier, or I squared is equal to -1. And these two are actually synonymous definitions. Well, actually not entirely. But basically I, and this is kind of the issue with the square root of a negative. There is no number that can square to produce a negative. And that's why a lot of mathematicians were like, okay, this is stupid. You can't actually square a number and get a negative. It's impossible because when you square something, it always comes out positive. But that's the genius behind I, is it is the solution to that unsolvable problem. No real number can square to be a negative, so we'll invent I, and we'll let that be the mysterious algebraic solution to the number that can square to produce a negative. And the reason why a lot of mathematicians probably didn't like this is because they didn't like that you could be so cavalier and just saying, okay, let's just make up I and let this work. But it turns out that the algebraic significance of the imaginary unit cannot be ignored, and the presence within equations helps us to see that it's not imaginary and the significance is real, even though we call it imaginary. And it took a couple hundred years before mathematicians all kind of agreed, okay, this is useful, and it sort of permeated into the mathematical zeitgeist and just became a number that we use so regularly. But it's definitely one of the more complex, again, I'm not trying to be punny here, one of the more complex types of number systems that we use as well. And very famous mathematicians such as Euler and Gauss really formalized I within their equations and sort of popularized its use, as well as with the development of calculus, not exactly hand in hand, to the field of what we call complex analysis, which is the study of complex numbers and how we use them. It's one of my favorite subjects. I've always found it quite interesting because of how different it is. And actually, I thought that this quote from Gauss was really enlightening to what I've been talking about the historical significance of I. And actually, if you read the quote, it's so ancient, but I'll go ahead and read it. It says, if this subject has hitherto been considered from the wrong viewpoint and thus enveloped in mystery and surrounded by darkness, it is largely an unsuitable terminology which should be blamed. Had positive 1, negative 1, and I, the square root of -1, instead of being called positive, negative, and imaginary, again, as we call the number imaginary and negative, or worse still, impossible. This was a phrase a lot of mathematicians said is it's impossible to do this. Had been given the name, say, of direct, inverse, and lateral unity, there would hardly have been any scope for such obscurity. Now, these are terms which, unless you're a mathematician, might not resonate with you, but direct unity is often a term in math which we use to describe one as like a unit, like each number on the axis is a unit, unit by unit, sort of like when we don't have meters, we just say it's 1 unit long or 2 units. And so often 1 is kind of like the foundational direct unit. And so, Gauss is sort of saying here that these names, positive, negative, and imaginary, are partly to blame for the mystery surrounding these types of numbers. And he proposed that negatives could be called inverse unity, because and really between positive and negatives, there's the idea of oppositeness behind right, left, positive, and negative is very critical, and that's kind of the idea of a mathematical inverse. So inverse unity would kind of be, instead of direct unity in the positive direction, inverse unity. And lateral unity, it's kind of hard to explain why this makes sense for imaginary numbers, but imaginary numbers can actually be graphed within a secondary plane called the complex plane, and it basically transcends the real number line, and those numbers can be graphed and understood graphically, even though imaginary numbers don't show up on the graph when we're graphing parabolas or whatever. Anyway, sorry, I'm getting way too deep into this, but I thought that was an interesting quote. But sort of to summarize everything I'm saying, imaginary is not a very good term for these numbers. They are very important. They're not just made up baby stuff. And what I wanted to show you is where these numbers, sorry, this video is getting really long, but I think this is such an important thing, which is why I'm going on about it. But basically, the imaginary unit and the imaginary number, it shows up all over in all sorts of different fields. Most times in calculus, you don't work with imaginary numbers. So in this class, one of our primary goals is to understand the math needed for calculus. I is something you're not going to really deal with in your calculus course. But if you're studying engineering or other advanced sciences, or if you're going to get any sort of study in higher level math, I is going to be really important to more advanced calculus, differential equations, signal analysis, geometry, algebra, number theory, complex analysis. And one of the most pivotal formulas in complex analysis is often referred to as Euler's formula, which is my favorite mathematical formula, which relates exponential functions raised to a complex number to trigonometric functions. And this formula, to those who have never seen it before, it can seem really, really unusual and hard to really understand and believe that it's true, but it's really, really cool if you really analyze it further. And that, that's a foundational formula in complex analysis. Now in physics, I can be found, again, all over the place as well. Electromagnetism, it's a very common construction within their equations. Electrical engineering, circuit theory, it's all over the place. And I thought I'd mention that in physics and engineering, often they use J instead of I, because I is often used for current, and they don't like to reuse letters. So sometimes J is used instead. It doesn't really matter what we use to describe it. We just don't want to confuse it with something else, which is named. Quantum mechanics, relativity, the study of how things move at very, very fast speeds, and all of those sorts of branches, all littered with I. It's all over the place, as well as fluid dynamics, the study of how fluids move when in a pipe or in a turbine or whatever. But Schrödinger equation is Schrödinger's equation, an equation you've probably heard of, or Heisenberg uncertainty principle and Heisenberg matrices. These are very, very, in the last couple hundred years, some of the biggest developments in all of physics. And I just wanted to show you those equations and show you, well, there's a whole bunch of components within, and a lot of these things are stuff you learn what these mean in calculus, or physics in general. But notice that the imaginary unit is actually present in this equation. It's just sitting right there. And so, the importance of it cannot be stressed enough. Some of the biggest breakthroughs involve imaginary numbers, as well as looking at the Heisenberg matrices. You can see I is all over the place. So anyways, I'm going to end my rant on the imaginary numbers. In the next video, we'll talk more about polynomials and how we can deal with imaginary numbers, factor them, and actually break them down with using these number systems.